Hello IROS 2021. I am Micah Corah. Today I am presenting my paper Scalable Distributed Planning for Multi-Robot Multi-Target Tracking. This work was a part of my thesis while I was a student at CMU, advised by Professor Nathan Michael. Presently, I am a postdoc at the NASA Jet Propulsion Laboratory. So why should we care about localization and tracking problems? One application that I'm interested in is urban search and rescue. In this domain, robots can provide valuable situational awareness to first responders, such as by providing maps of the environment, assessing hazards, and locating survivors. Subterranean search and rescue is also the subject of the DARPA Subterranean Challenge, and I have been involved in the competition with Team CoStar at JPL, as shown here. Aerial robots and localization tasks are becoming increasingly prominent in rescue efforts. After the recent Surfside Condo collapse in June 2021, rescuers flew more than 300 drone missions through the duration of the response. In addition to producing detailed maps, the increasing scale of drone operations also leads to increasing scope, including locating, inspecting, and even retrieving objects in the structures and rubble. Examples from the response include searching for survivors, reading license plates to identify residents, searching for pets, and documenting presence of belongings in the rubble. The author of the referenced article, Professor Robin Murphy, points out that being able to localize objects in the rubble is an important capability that was missing from the response. In general, target tracking methods build on a wide body of work. Related topics on state estimation include distributed Kalman filtering and RF-based tracking methods, and recently vision-based tracking and detection methods based on convolutional networks such as YOLO are becoming increasingly attractive while also broadening the scope of what tracking systems can do. Then, given methods for detection and estimation, designers can choose from varied methods for control, trajectory optimization, and informative planning. However, I will not go into detail on these topics as the focus of this work is on scalable multi-robot sensor planning. Greedy sequential planners are frequently applied to multi-robot perception and information gathering problems, including target tracking. This approach consists of maximizing perception objective in sequence across a series of robots, each time conditional on prior decisions. Greedy planning is often preferred due to simplicity in implementation and for providing suboptimality guarantees for objectives of relevant problems. This approach can also extend general single robot informative planning methods to multi-robot settings, and approximate and anytime approaches are common. Now, let us discuss scalable planning for target tracking and how greedy methods scale to large numbers of robots. Although greedy methods are common in target tracking and informative path planning problems, they do not necessarily scale well to large teams tracking many targets, and naive attempts to parallelize such distributed planners can produce increasingly poor suboptimality guarantees. Our prior work builds on this analysis of distributed planning to produce a scalable randomized coverage planner called Randomized Sequential Partitions, or RSP, and this paper will extend RSP to more general target tracking applications. However, there are also other approaches to scalable sensor planning. Sung et al. Present a min-max formulation that is applicable to coverage-like problems, yet their linear programming approach would be difficult to extend to include more general objectives or more advanced single robot planners. To summarize, anytime and approximate planning methods are common in target tracking and sensing problems, and scalable distributed planning methods are generally limited to relatively simple coverage-based problem forms. To address this gap, this paper presents a scalable distributed planner for multi-robot target tracking that applies to approximate and anytime planning with a general class of objectives. This work has three main contributions. The primary contribution is a scalable distributed planning approach for general target tracking problems. Toward this end, we present analysis that quantifies inter-robot redundancy for mutual information in target tracking problems, and we apply this analysis to our randomized sequential partitions, or RSP, planning approach. Our analysis also takes a slightly different approach than related works. Rather than assuming robots plan with fixed suboptimality, our analysis accounts for anytime planning and other approximations in terms of average suboptimality instead of worst-case behavior. Please refer to the paper for more detail on this topic. Last, we apply our approach in simulation to a simple multi-robot tracking problem. Since we are interested in how our distributed planning approach scales to large teams, we present results for as many as 96 robots, where RSP Planner provides a 24 times improvement in the number of sequential planning steps compared to conventional greedy methods. In the target tracking problems we study, robots obtain conditionally independent observations of some or all targets at each time step, and the robot's ability to sense targets decreases with distance and approaches zero asymptotically. The target's dynamics are known and independent, and our assumptions ensure that target states remain independent in spite of the robot's observations. Additionally, the number of targets will be proportional to the number of robots, and the goal will be to select actions to minimize uncertainty or entropy in the target positions or other aspects of their states. Our approach to target tracking involves solving multi-robot receding horizon sensor planning problems. When I talk about receding horizon sensor planning, what I mean is that robots select control actions or motions to jointly maximize sensing quality for camera views or range observations over a short time horizon, say a few seconds. After planning, robots execute only the beginning of the finite horizon plan, and the horizon advances in time as the team replans. Our receding horizon planners will maximize mutual information between the robot's observations and the target states. For the purpose of this presentation, it is not important to understand the details of the mutual information objective, except that the mutual information objectives we study are compatible with greedy planning and that maximizing mutual information minimizes uncertainty. Additionally, we will take advantage of how the mutual information can be written as a sum over targets thanks to independence in target states. We solve these receding horizon sensing problems by sequential greedy planning. Robots plan in sequence and maximize the sensing objective given access to the other robot's prior decisions. The process proceeds like so. The first robot in the sequence plans for itself to maximize the sensing objective, as seen here. Then, the second robot maximizes this mutual information objective given the first robot's decision. The third plans given the previous two decisions, and finally the fourth plans with access to all the prior decisions, and so on. Although this algorithm is simple, planning sequentially guarantees that the mutual information is collectively within half of optimal for all the robot's selected actions. Although half may not sound like much, the best possible suboptimality guarantee for any polynomial time algorithm on similar problems is only somewhat better at about 63%. If we represent access to other robots' prior decisions with edges in a directed graph, sequential planners form complete directed acyclic graphs as shown here. Specifically, each robot has access to the decisions by each prior robot in the sequence, and therefore there is one edge from each prior robot. These edges also produce temporal constraints. Each robot must wait to begin planning until it has received all prior decisions. As such, the planning duration must grow with the number of robots, and even latency in communication alone quickly becomes significant. However, if robots ignore some of the prior decisions, we can obtain greedy planners where some robots plan in parallel. Specifically, if we partition the robots into groups like so, and remove the edges within each group, we can produce planners where these groups of robots plan in parallel, as shown here. Planners based on our randomized sequential partitions approach assign robots to groups randomly, and this allows us to amortize the cost of ignoring decisions via an expectation. So in RSP planning, robots initially assign themselves randomly to one of n sequential planning rounds, illustrated here with different colors. Robots in the same round, that is, with the same color, plan in parallel, ignoring each other's decisions. Meanwhile, different colors plan in sequence with access to decisions from prior rounds. This addresses a key limitation of conventional sequential planners. Rather than having one sequential step for each robot, we have a fixed number of steps for any number of robots. Even when only considering coverage-like objectives, RSP planning is readily applicable to a wide variety of sensing and perception problems, as in the exploration scenario shown above. This simulation is also based on a distributed implementation of RSP running in ROS. When we analyze RSP planning, the suboptimality depends on a notion of redundancy between robots, shown here with the intersection of two observations for an area coverage reward. It is relatively easy to characterize redundancy between two robots when we are working with the coverage objective, because with coverage, redundancy decreases monotonically in the presence of prior observations. Here, the effective redundancy between two robots, the area marked by A on the left, decreases due to an observation by the robot shown in red, producing the smaller area marked B. As such, the initial redundancy between the two robots produces an upper bound on the effective redundancy at any point in the planning process. However, this redundancy is not as well behaved for the mutual information objectives we study in target tracking problems. The challenge with quantifying redundancy and information gain for problems like target tracking is that observations can interact in more nuanced ways than they do with coverage. Consider this example of robots observing targets from different positions. For individual observations, each of the robots can gain a significant amount of information about the target's position on their own. However, as we combine observations in these two scenarios, we get different behaviors in terms of information gain and redundancy. On the left, robots observing from different directions obtain high information gain from nearly independent observations and have low redundancy. But on the right, the second robot only incrementally reduces uncertainty in the target's position, and the redundancy between the two robots is high. However, for our analysis, we are interested in how redundancy between pairs of robots depends on prior observations by other robots, and phenomena that are similar to what I have shown here can cause the redundancy to fail to decrease monotonically in the presence of prior observations. Seeking to bound redundancy between agents for target tracking, we can look at worst-case behavior, which is that the mutual information is totally redundant, but only for observations of the same target, thanks to independence between targets. As such, we can bound redundancy between the robots on a per-target basis, which produces expressions like the one I have shown here. Looking a little closer, we can see that the redundancy for a target is small if the information gain for either robot on its own is small. For example, if a target is distant from one or both robots, that target will generally have a small contribution to the redundancy. Likewise, if two robots are very distant, their observations will generally have a low redundancy. These bounds on redundancy allow us to make statements about RSP planning performance. First, suboptimality approaches the original guarantee of 1/2 with 1 over the number of rounds. The suboptimality guarantee is independent of the number of robots if the total redundancy per robot is constant, which requires some additional assumptions. Last, our planner is run in constant time after taking advantage of range limits and sparse phase filters. We present simulation results for target tracking problems scaling from 8 to as many as 96 robots. Robots obtain range-limited observations of the distances to targets with Gaussian noise and plan by a Monte Carlo tree search. There's 1 target per robot, and targets move randomly on the grid. And in this problem, the robots again seek to minimize uncertainty in terms of entropy in the target's positions. In our first set of experiments, we compare RSP planning with various numbers of rounds and range limits to other potential planners. We find the entropy quickly approaches that of sequential planning for planning with only a few rounds, and providing significantly better performance than if robots were to plan myopically without explicit coordination. Now let us consider system behavior at larger scales. Here I have plotted objective values and redundancy weight per robot for range-limited RSP planning with 4 rounds for up to 96 robots. At this scale, RSP provides a 24 times reduction in the number of sequential planning steps compared to a fully sequential planner. As we can see in this plot, the objective value per robot in orange appears to approach a constant value, and the redundancy in blue appears bounded. In general, the combination of asymptotically constant objective value per robot and bounded redundancy is sufficient to guarantee constant factor suboptimality for any number of robots. To conclude, in this talk I have presented a distributed planner for multi-robot multi-target tracking based on randomized sequential partitions. Our approach enables scalable multi-robot planning for target tracking problems with general objectives and planners. To do so, we have presented analysis that bounds redundancy and mutual information for target tracking problems. And most importantly, we demonstrated that the total planning duration scales well and is often constant for large numbers of robots. Future works may apply similar analysis to multi-robot sensing problems or study more nuanced scenarios and environments, such as arising from search and rescue problems or as in the DARPA Subterranean Challenge. Likewise, we may consider implementation of these methods alongside modern vision-based tracking systems. Thank you for listening. I am Micah Corah, and this concludes my talk.